Okay, so this is again part of the classical mechanics series. So this is where we study more advanced mechanics. We're starting at the beginning here, so let's just talk about the fundamental nature of force and motion and introduce some new notation. So let me start off with the following. Let's say I have some position, some vector position r, and that's the location of that. If I look at how that position changes, that is the velocity. So we could say velocity is dr dt, and you can take the derivative of a vector as I showed in my last video. One of the things that we're going to sometimes write in order to make notation a little bit better is this dot notation. So I can say the vector r dot, where the dot represents a derivative with respect to time. So this is equal to the derivative of r with respect to t. Now, this, I'm not really happy with this, having a vector and a dot, but sometimes you just got to do stuff like that. In one dimension, the dot notation works really well, and we'll do that too. Now, what if I take the derivative of the velocity? So I say the acceleration is the derivative of the velocity with respect to time, which is the derivative of r dot with respect to time. Well, now I take the derivative with respect to time of a derivative with respect to the time, and I get r vector double dot. Okay, so that's the acceleration. That's a, that's v, and r is just r. Okay, so that's just dot notation. So the dot. Now, in other fields, they may use the dot to represent derivatives with respect to other variables, but in physics and in mechanics, we're using the dot to represent a derivative with respect to time. Okay. Now we have Newton's second law. So this is says the following: F net equals ma. So if I write, that's a vector. If I write this in dot notation, it could be m v dot, or it could be m r double dot. Now, we do have another variable. We have the definition momentum, which is mv. So if I look at this right here, then I can also say F net equals p dot. So if the mass is constant, this is actually a little bit better form because it doesn't assume a constant mass. If the mass is constant, then this could be written as, let's write it out the long way, d dt of mv. But if the and using the product rule, then this would actually be dm dt times v plus m times dv dt. So if the mass is constant, that term's 0, and you get m dv dt or ma. So they're equivalent. Okay, now let's look at one dimension and let's rederive the kinematic equations. So in 1D, so here I have an object in the x direction, and it has some force on it, F net. It's not a vector, okay, because I have in one dimension. So it could be a positive or negative. And this is my value x. So if I write Newton's second law, I get in one dimension, I get F net, let's call it Fn really, equals mx double dot as a function of t. So if I solve for x double dot, I get x double dot equals F net over m, and that's a function of t because the position's going to change, maybe the acceleration could change. In fact, x double dot has to be constant if the force is constant, but the force doesn't even have to be constant really. Okay. So how do I get an expression for x as a function of time? Well, let me write this as d dt of x dot equals Fn over m, because d dt of x dot is x double dot. So now I'm going to multiply both sides by dt, and I get d x dot equals Fn over m dt. Now I have, this is actually a differential equation, but I have separated the variables, so I only have terms that depend on x dot over here and only terms that depend on time over there. So now I can integrate both sides. So if I integrate this side, the integral of dx is just going to the integral of x dot is just going to be x dot. And the integral of this constant times dt, assuming it's a constant force, is going to be Fn over m times t. But I have to have a constant in there too, because I don't have limits of integration. So, and you could do this in a lot of different ways. And I probably should. But, so now I can say x dot at a time 0 is going to be equal to F over n m times 0 plus c. So that means c has to be the velocity at time 0. So let's say c equals v0. So now I get x dot as a function of t equals Fn over m t plus v0. Now we need to do it again to solve for x dot. So I'm going to say d dt of x, that's x dot, is going to be equal to Fn over mt plus v0. Now I can again multiply both sides by dt, and I get dx equals, let's write it, Fn over m t dt plus v0 dt. And now I'm going to integrate both sides. So this side I get x as a function of t. This side now I have Fn over m t dt. If I integrate that using the power rule, I have to add 1 to the power and divide by the power. So I'm actually going to get 1/2 Fn over m t squared. And then I have v0 times dt. So it's just going to be v0 t plus c2, the next constant. And then again, I can do, if I put in t0, this term goes away, that term goes away, so this has to be the position at x equals 0. So I get x as a function of t equals 1/2 Fn over m t squared plus v0 t plus x0. And that's your kinematic equation. So you actually don't even need calculus to derive that. There's another way to do it, but I just wanted to show you how you use this as a differential equation to integrate and define that. Okay, so we'll do another problem with forces, and in particular show how momentum is conserved, and I'll do that in the next video.